Okay, so you probably heard this, but I don't know how many of you are seniors, but it looks like the vaccine is working really well. The one from Pfizer. There are many vaccines, of course, but one of the more promising ones is working great. So that's really fantastic. But in any case, so we're still having to deal with doing things online. I did look at the possibilities for the exam. I'm going to actually send the class an email for an app that was done by a faculty here. I haven't actually tried it out, but it might help with the right-hand rule business. So I'll send it to you guys. I don't know. I haven't checked it out. I'll check it out. But unfortunately, we don't really have another class before the exam. The exam is, as you know, is 1 week from today. But we have Veterans Day on Wednesday, so we won't have class then. I'll send the app, and I haven't tried it out. I don't know if it will help or won't help. But in any case, I'll send it in case somebody finds it helpful somehow. I didn't check it yet. So I think it's something about visualizing 3D, the vectors in 3D or something. But yeah, there is a lot of that in the exam. I've decided what I'm going to do to sort of put a little bit more stress on the time. But again, the final, I will try to give extra time. But in this class, I'm constrained by the time of the class. So the best thing I can do is tell you which problems are going to be the long format problems. But I'm going to have a bunch of multiple choice problems. And in the multiple choice problems, you will keep having to do this right-hand rule. To find forces, to find B fields. And remember that if you take it seriously, we did 3 different right-hand rules. Actually, there were only 2 in the end that were used more frequently. The one about whenever there's a cross product, that's the one right-hand rule. You use your right hand. And then please remember, this shows up in the exam. multiple times. If you do your right-hand rule, and then you decide, is there a Q in there that I have to worry about, a charge? And if the charge is negative, then I reverse whatever I just did and flip it. Instead of using the left hand, I just do it with the right hand, but then flip it. So please keep that in mind, otherwise you're going to get multiple questions off by that factor of Q. So a minus is an electron. So you're going to have to flip it because it's an electron. So that will happen several times. Now I did decide to do more multiple choice, and so not have you spend a lot of time with the long format. I'll probably do that in the final as well, but I haven't decided about the final yet because that's the time is different on that one. So no, let's for the third exam there will be I want you to spend more time in the multiple choice and less time in the long format problems. So the long format problems are these. I told you 2 wires and they carry a current. So this is the stuff we were just doing. So there's definitely going to be a problem like that. So 2 wires that have a current. So then I can ask you the B fields of the wires at different points in space, or I can ask you the force between the wires. Okay. So today is the only chance for office hours. So I'm going to give you, I'll try to do a few things that I think will be helpful. But if some of the things I say you feel like, oh, I forgot that, I'm gonna screw it up, I'm gonna spend too much time, then yeah, feel free to stay for office hours today. Strategically, again, there are some days that office hours might help a lot more. So since we don't have class Wednesday, it would have to be today. So whoever wants to stay for office hours today, that's fine. Let's do office hours today. Makes sense. Office hours online never work as well as in person, but that's what we have going. So this is the time to do it. Right. So the 2 wires, we said that would be in there. Then we're gonna have, like when we had a bunch of capacitors, and then you had to put find the equivalent capacitance of the circuit. So I'll remind you of some of that today. But in this case, it's not capacitors because capacitor was in the previous exam, but still we should do the same thing over again, but with resistors. But it's kind of like the same kind of problem, but now it's resistors, not capacitors, because we've never included resistors in the previous exam. So a bunch of resistors, series, parallel, you have to find all the voltages and in the circuit and so on. So find the equivalent resistance of the circuit and then find currents in different places. Now, you could do that with Kirchhoff's rules, which is the first thing I suggest we can do a problem with. But again, if you can do it, you can do it faster by doing the equivalent resistances and so on. It's up to you. Again, it is a little bit time constrained. So you probably want to use, for the problem about series and parallel, you probably want to use the rules for series and parallel, not Kirchhoff's way. But there will be a separate Kirchhoff problem. So there is one that is just resistors in series and parallel. And then you have to find the equivalent resistance. Okay, so that's another one. So 2 so far. Now I'm going in line here. You have a magnetic field and you have a charge, the one where the charge is moving in circles. And that's the case where there's a magnetic field and there's a moving charge, so there is a force because the charge is moving. So remember, the formula for that was force equals charge Q, the velocity of the particle across the B field. And so you'll have to figure out that problem. I can connect that with another piece and so on. I'm not gonna, there's a problem like that. It's not very hard, actually, that one. But there's a problem where there's an external magnetic field and there is a charge moving in circles. Okay. Then there is a Kirchhoff's laws problem. Once again, that's not going to be any kind of challenge. That's just to make sure that you know the rules. So I think we should start with that. Make sure that right now, that after this, that you can solve the circuit. The circuit is very easy. It's not even a complicated circuit. It's a very easy circuit. And I'm actually going to tell you that you don't have to solve it. I'm going to suggest we solve it in this case. do it together to make sure everybody gets the right numbers. And just by getting the right numbers, you know you did exactly the right thing. But in the exam, you won't have to solve for the currents. Don't have to do it. So you just set up the equations. As long as the equations would give me the answer, if I did solve your equations, I will get the right answer. You will get full credit for doing that. It's just the equations. I will save you a lot of time of playing around with things and then making a mistake at the end and kind of ruining things, even though you knew everything. So you won't have to do any of that. That will save you time. Okay, so we'll start with this one and in a second. But anyway, and then which one was it? And then the one about the loop. We just did that the other day. I don't think we should do that again. We just did it. You have a loop. There's a magnetic field, and you move the bar, and you're increasing the flux, and then it's Faraday's law, and then you have to figure out what is the current, what is the EMF, what is the current, how much power is dissipated in the resistor. We just did that in the last class, so let's not repeat that. Let's start with this, I think. I have a few other things to talk about. I have a few things that will help you with the multiple choice questions. But let's start here, and again, it will work better, the class today, if you do most of the work, and then we can see if you got it right. Okay, so the answer to this problem here is right below, so I can show it immediately. But please put it online, put your answer on chat, just to try to do it all the way through with the numbers, everything else. Let's see, just to force you to try to solve this circuit using Kirchhoff's rules right now. And you're supposed to find the three currents, I1, I2, and I3. The problem in the exam is not any harder than this, and you don't even have to solve it. So that's not going to take a long time. But you could, if you put the wrong signs, of course, then yeah, you will lose a bunch of points for no reason, because you should just learn the rules. And okay, anyway, so give it a try, and just for this practice, find the currents, and then see if we agree on the currents. Okay, so when you find the currents, put them on chat. See if the entire class agrees. Oh, by the way, just again, just for clarity here, when I put the exam question, I'm not going to tell you the direction you're supposed to go around the loop in. And I'm also not going to tell you the directions to pick for the currents. That's up to you. What I will ask you in the exam is clear up your diagram and write the equations for your diagram. Okay, so you will choose directions for the currents, and then based on that. But in this exercise, just to be on the same page so that we can go fast through all the signs and see that we agree on the signs and so on, please choose for your equations, choose the same directions. So that I don't have to do, because I don't know which directions you chose. Otherwise, I can't see. So I can't start debating signs when I can't even see what the directions you chose. So just choose these same directions: I1 going down, I2 going down, I3 going up, and then also use the same loop directions as well, just to make it easier to check your work. But you don't have to do that in the exam. But I'm just to make it easier now. Just choose what's there. Nobody has them yet. If you, as soon as you get it, if you want to share it so other people can see if they get the same thing. Well, Isaias, that's the thing. It's better to get the answer, because then if you get the right answer, you know you for sure you did it right. But yeah, I'm going to show you the equations in a second. But yeah, the whole point is just to get the answer this time. But you won't have to do that in the exam. But it's just easier for me to see your answer than look at your equations. Certainly everybody's equations I will have a hard time with. My first idea here is to see how many people get the numbers correct, to get the idea that, do you know how to do it already? We can go through it. We have time. So whatever we need to do, that's what we're going to do. But let's see if it works. Okay, thanks, Emma. Anybody else has different numbers, same numbers? Let's give you a little bit of time. Again, this will totally, it's okay, it doesn't matter, it's fine. I don't remember the answer, so I can't tell you, Emma, if that's correct or not correct. I have to wait until I scroll up. It's here below. But if anybody else can tell, can tell us if they got the same thing. What I was saying is that for sure this will pay off. This is not a situation where you're going to do a lot of work and it's not in the exam. This is in the exam. Isaias, if you want to, go ahead. If you want to rather put the equations instead of the answers, go for it. Write whatever you want, and then we can see what happens. I'm trying to wait for other people to catch up and so on, but yeah, you can write the equations if you prefer. Whatever you want to do is fine with me. Nobody else? Okay, Isaias, you have three equations there. Now you already wrote them down. Of course, we can check those. But you have three equations and three unknowns. So it should be possible for you to find the currents. Right? So if you want to find the currents, go ahead. If you're done, then you're done. Somebody else wants to write, nobody found the currents? Yeah, it takes a little bit of time, yeah. But three equations, three unknowns is not super terrible. Should be possible to do. Okay, Jason, go ahead. That's what's in the exam, so go ahead if you want to. Just write your equations down, that's fine. It's a little harder to check, but does everybody agree with Isaias? Okay, let's do 5 more minutes. But if you're having trouble remembering the sign rules and all of those things, then yeah, please practice it a little bit. I'm gonna move along in a second and show you the answers. This works a lot better if you try it. and try to get an answer. Does everybody agree with Isaias? He wrote the equations there. Anybody else got something different for the equations? I'll just wait a couple more students to. Okay, in this case, we're gonna do it in the same direction as is drawn in the diagram. Already is well defined. It doesn't leave any choice for any room for your own choices. So basically, it's already choosing the direction of the current. Okay, so if you are having a hard time with this, that's an example. You know it's going to be in the exam. So that's just an example of, this is not supposed, there's no trick here. It's the stuff we covered. Okay, so let me, because we got to do a few other things. There's not that much in the end because we just finished the part about the two wires, and so we can save that for office hours after class. So there's not that much really that we have to cover during class. We've done almost everything already. But there are a few more things that I can remind you of. So yeah, let's move ahead then, because there are a couple of other things that I did want to go over. So yeah, okay. So again, this is not supposed to be a problem where you spend a lot of time. If I did force you to write the currents, then yeah, I can see how you can see that you're taking quite a while here, just for just one problem. But just to the level at which Isaias did it, let's see what happens. Okay, so these are the solutions. Now I assign numbers in there, so they write the equations right there. I assign the same numbers in the drawing there. So look at the equations here, and notice the equations that Isaias wrote. They have the same signs for everything. Now the first one, that's the junction condition. He just put the I3 on one side, but that's correct. So the signs that Isaias had were correct. I'll go over how to get those equations again, if somebody's not quite clear about that. But those are the correct equations for everything. So what Isaias put up there, that's correct. For all the signs, there is no ambiguity. Once you've defined the current directions and you know how you're going to go around the loop, then you know the sign of everything, and it has to agree one by one. Once you've made your choices, then it's clear what you have to write. So you can see that the signs here agree exactly with the signs of what Isaias wrote above. I'll go over those signs again, but let's see. Let's get to the actual numbers, like Emma. Let's see if Emma got them all correct. I don't know. It's here at the bottom. Let's see. Oops. Is that what you got? I actually didn't solve it myself. I just got this from here. It doesn't seem to be the same. One thing I would say about this, so Emma, I guess I'm not really sure. Yours look a lot bigger. I don't know what happened. I would have to look at it. Oh, I see. You had different equations. So, okay. So let's go over the signs for the equations in a second. But these are the solutions. So, of course, they have three equations, three unknowns. So, of course, they can solve for everything. I'll post this on Canvas, but, it's not. But notice what happened again. You just put down the equations depending on whatever you drew, and they draw something, then you just write the equations. Then you solve the equations. Remember, we had this issue at one point. There was a multiple choice question. We had the wrong sign for that. Trust me, that was the problem with the multiple choice question. Okay, so the procedure is very clear. You just set some directions for the currents on the resistors, and then you solve your equations, and that's it. And if your current that you chose, the current direction is wrong, that just means one of these currents will come out negative. Instead of giving you a positive answer, we'll give you a negative answer. That doesn't make any difference. Okay, that's fine. That's just a negative current with respect to your choice, whatever your choice happened to be. Okay, in this case, they chose all the right directions, meaning, how do I know that? Because they all came out positive. So I know, therefore, that that is the direction of a current in each of those resistors. Okay, so let's remind ourselves about the signs again. And let me remind you how to do this. I'm going to start first with the junction. It does not matter which junction you pick. So let's do both. Okay, so we're going to pick this one. Okay, so whichever currents are moving into junction B, so I'm going to do B. Okay, so whichever go into B, I'm going to give it a positive. Whichever move out of B, I'm going to give it a negative. How do I know if it's moving in or out? You just use the current direction you chose. So if this is down, that means at the junction is going out. And it's going down through there. And it's going that way here. So if I'm picking this junction, then current 1 would be into the junction, into junction D. But if I'm picking junction B, that would be out of junction B. That won't make any difference. Okay, but we're going to do one sign for in, one sign for out. Sign for out will be negative. Doesn't matter. Sign into the junction is positive. So then you sum all the currents. So which ones are out? This one and that one. And this one is in. Sorry. So in is positive. So I3 positive. And then I1 and I2 negative. Minus I1, minus I2. And you add them all up with positives and negatives. And you add up to 0. Well, I can just move the I1 and the I2 on the other direction. I3 equals I1 plus I2. And this is how Isaias wrote it up. Is that the same he wrote? Yeah, absolutely. Isn't it? Yes, it is. Okay? So that's using junction B. Now we say, oh, what if we had chosen junction D? Where we would get in trouble then? Because that would be different. Well, let's see if it's different. So if we do D, then what would happen? What's moving in? Then what's moving in is I1 and I2. So I will write I1 with a positive plus I2 with a positive. And then I3 would be moving out of junction D. Minus I3 equals 0. Well, guess what? That's exactly the same formula. So you got the exact same formula, whether you use junction D or junction B. So it doesn't give you any new information to use both junctions. So you just use one of them, and that's it. You don't need to use the other one. It's the same thing. Okay? Okay. So you use one junction. That gives you this equation. Okay, great. So we're done with the junction. There's nothing else to say about junctions. You don't keep doing more and more junctions. You only do junctions if they're giving you more information. In this situation, one junction gives you all you need. Okay. So that's the junction rule. Great. So how about the other one? Well, again, we're going to use the direction chosen by, I deleted the, I'm still having trouble with writing. This was 8, right? And this was 1. Okay, great, 1 volt. Okay, so we start at some location, we go through the diagram, and then we come back. Okay, so if we start at B, then we first encounter the battery, and it's 1 volt. So we're going from the little one to the big one, so we're increasing voltage. So that's a positive 1. Now, based on our initial choice, when we're going through resistor 1, we're going with the current. So that means the rule was that if you go with the current, the positive is there and the negative is there. That's something that you are supposed to do in the lab all the time with measurement things. It looks like we're going to be able to do labs pretty soon again, but that's just, you can see it in the meter. That's easy to remember, but just write it for yourselves. If you go with the current, you go in the direction of decreasing voltage. So that's a minus 5 times R1. Okay? Oh, yeah. Sorry. 5 is the... Okay? Did he write that? Sorry, I'm checking that. I was saying, yeah, he has a minus. Yes, he has the same thing. Minus I1 times 5. Okay, correct. And here they have the exact same thing. We're doing the same order as the diagram. So we're supposed to get every sign the same because we chose the same things. So we're supposed to get every sign the same. So it's minus 5 times I1. Okay, now we continue the loop, we're continuing this way, but now when we encounter resistor 2, we're actually going against the current based on so we chose with the current to be negative, which is what you have to do, actually. That's not a choice. The choice is the direction of the current. But now once you drew the current, now you know the sign. So in this case, I'm going against I2 when I reach that resistor, so I need a plus 8 times I2. So that's that plus there. Okay? And that's the plus that Isaiah also put in there. And now I'm back to where it started, so that's equal to 0. Okay, so therefore, yeah, I don't have to keep writing it. That's the same thing that they got there. Now, we're going to do the same thing here at C. Notice now that when I go to the battery, I encounter the high voltage first. So I'm going from high voltage to low voltage. So I'm going down in voltage as I go around counterclockwise. I go from high voltage to low voltage in the battery. So that's why there is a negative sign right there. Then I reach this, I'm going around this way. I started here, then I go this way, I'm going minus, then I'm going with the current. So there's going to be another minus. So that's that minus. And then finally I go through I3, I'm still going with the current. So there's going to be yet another minus right there. So there's only one plus. There's only one time I went against the current, and that was on R2 and loop 1. Okay? Are these signs clear to everybody? You do have to do that. Okay, so what I'm gonna ask you in the exam is, I will check your directions for the currents. So I'm gonna ask you, please, just to make it easy on me, don't make me guess how you wrote your equations and so on. So it's much easier for me if you draw something that looks just like the drawing here, where you're telling me the direction of the current, and you're also telling me which way you went around in the loop. That will make it easy for me to check all your signs immediately. Of course, there's nothing, I could have figured it out anyway, but it just takes me longer if I have to guess what you did, okay? So if you just tell me which direction you picked and how you're going around the loop, clockwise or counterclockwise, then I can easily check your signs very quickly to see that that's correct for that. Okay, any questions about the signs? No questions? Okay. So let's do a few other things then. Let's see. Well, this one, there were several things that I wanted to do. This one I wanted to do. Let's save this one for a little bit later. Yeah, this one is not bad actually. There's going to be multiple choice questions like this. Let's do this one for sure. But before we do that, let me come here just to finish this Kirchhoff stuff. Okay. This part is what we just did. Notice, by the way, that in some drawings they draw this a little different. You see how they do the battery a little weirder? Some people like to draw batteries that way. Okay, but in any case, the low voltage is here, high voltage is here. Okay, it's the same thing, but they draw it a little weirder. But it's the same thing. Okay, so actually, maybe the drawing I got from, maybe it looks like that, but I got a drawing from someplace. I think mine has like those because I got it from someplace. I didn't do this from scratch. But in any case, it's the same thing. It's a battery and then currents and so on. Okay, so this is the case we just went through. There's nothing here that is any different. They're just solving for things. Okay, here is an example of the minus sign I told you about. Look what happened here. You don't have to solve this. We just did this, but I just want to show you what's going on. So they chose directions, this direction, that direction, that direction. And then they have voltages. Well, the fact is the directions of the current will eventually depend on what voltage you're talking about. So in general, if you just pick directions, you might get it wrong, but it doesn't matter. And they do get it wrong. Look, they got an answer. They got I2, they got I3, but they got minus this much for I3. So what that means is I3 is not really in that direction, it's in that direction. That's what that means. But so what? One of the three was actually flipped. You see, of course, it had to be flipped. Think about it. When they did the junction rule here with this way, they got is minus, minus, minus. Oh no, because they have I1 going in. No, sorry. Anyway, it's flipped. I was going to say something that's not true, but that's flipped, meaning the I3 was going the opposite direction of what they chose. Okay, so what? That doesn't make it. So don't worry about it. Just choose directions. Don't worry about which way it should go. You could even do it randomly, you know. And again, you could do it. What I was trying to say is that it would be okay to have a junction that looks like this. If you have junction, you have currents, and the currents come all out of the junction. That's not going to cause you any kind of trouble. That would give you minus, minus, minus. So it would be minus I1, minus I2, minus I3 equals 0. So obviously, one of those currents will come out negative in the end. One or more of the currents will come out negative. But so what? Your condition based on your currents, you have to write it this way. If that's your currents, I1, I2, I3, then that's your condition. Okay, that's it. Minus going out, plus going in. So based on that, based on the way you drew it, this is the condition you get. And then you solve it. And then you get whatever you get. And that's your answer. There's no problem ever. So don't second guess yourselves at any point. Just start doing and then get done, and that's it. Move on. Okay, here I wanted to show you, actually this is a capacitor problem. There is no capacitor problem. This was included in the last exam, so this is not part of it. But we did have RC circuits. Now I haven't done I'm gonna do a multiple choice question on RC circuits. That was kind of a section in the PowerPoint. We didn't spend a lot of time on it, so I wanna go through an example here to make sure, and I'm going to include a multiple choice question that is similar to what I'm going over right now, because it's fair to ask this, but we didn't spend a lot of time on it. So I want to go through it right now so you figure out how to analyze those kinds of situations. We did talk a little bit about it. We said, okay, how about charging or discharging circuits? Okay, so let's go through that right now, figure out how this would work. What is the value for the charge and the capacitor and so on. So this is the business about RC circuits. So let's see what they're telling us here, and I'll include something similar to this, just one multiple choice question similar to this. Okay, so we'll analyze it based on what they give us here. So they say, okay, it depends for each instance. It depends what you're talking about. What are you doing? Is your capacitor initially charged? Or is it a discharge and you're trying to charge it? What's going on? Okay, so let's just see what they do here and see how we would analyze it. So in this case, what they do is they start at some time, they have a circuit. And they have the position A for a long time. Okay, great. So what they're saying is they start out with the circuit like that. Okay, so they don't have, this part doesn't connect with B, it just connects like that. So, and then they wait for a long time. Okay. So what would happen if you wait like this for a long time? What would happen? What would be the current in the circuit for after a long time? Everybody agree with that? So what's happened? Yes, that's correct. You put a battery, so you have it for a long time, you put a battery across a capacitor, and then you let it charge and charge and charge, and finally it's fully charged. At that point in the long time, we did go over this, but let's just remind ourselves a little bit so I can put that multiple choice question and it won't be a total surprise to you. So what you're doing is you're hooking a battery across a capacitor. Now, once the capacitor is fully charged, that will take a very, very long time, actually an infinite amount of time, but in practice, you wait long enough and that's essentially it. So then you just wait for a while and then you're fully charged, meaning the current goes to zero. If the current goes to zero, then IR equals zero. So there is no voltage drop across the resistor, right? So after a long time, the current dies, and there is no voltage drop across the resistor because IR is zero. So therefore, the voltage drop in the capacitor will equal the voltage of the battery. Okay? So then if you want to know how much charge there is at time t equals zero on the capacitor, then you know how much charge because you know that the definition of capacitance is the charge divided by the voltage, right? So if you want to know the initial charge, that would be Q equals the capacitance, which is a number, times the voltage across the battery, which is the same as the voltage across the capacitor. So now you know the initial charge in the capacitor. Okay. So now they say, what is the current? So let's go step by step, make sure we agree on everything. Say, what is the current in the resistor just before the switch is thrown? Well, initially, you allowed the capacitor to fully charge for a long time. The current was zero. Now you flip the switch. Right before you flip the switch, the current is zero. Okay. Now, right after you flip the switch, what is the current? Well, now you have only two things. Now you're here. Now you flip the switch. So you're here. So you have a capacitor that's fully charged, and you know the charge in the capacitor. And then you have just the resistor. So you're always, in essence, you're always actually doing like Kirchhoff's rules. You're going around the loop and you know the voltage. So you know the voltage across the capacitor, which is the voltage in the battery at time t equals zero. And you know the voltage. So all of a sudden you close the switch and then all of a sudden the current will jump up. And at that point you must have, right after you cross the switch, what you must have is IR equals VC, which equals VV because the capacitor was fully charged. Okay? So therefore, I equals V over R. V is 12 volts. So then you get 12 volts divided by R is, why does it have watts in there? Okay, they mean omega, they mean watts, ohms. Okay. Anyway, you divide 12, what was it? 12 by 20? Okay, you get that. Okay? You see how this is working out? Okay, next. What is the charge just before the switch is thrown? Okay, great. So C times V. We said that right here. V is 12, C is 10 microfarads. There is the charge. So right before you flip the switch, this is the charge on the. So now they're going to ask you one last thing that maybe is the hardest. So far, it's just a matter of, if you notice, we're doing loops. We're doing a loop when the switch is one way, and then we do a loop with the switches the other way. So the loop changes depending on which side the switch is on. Okay, now they're asking you, so this is the total right after this. Okay, well, this is just a trick question. It's the same. Now you flip the switch, the charge is still the same, but now they're going to ask you, what is the charge after some time? Now, to be honest, in my multiple choice question, probably what I would do is ask this question only, not like everything else is fine, conceptual, just to make sure you understand every step. But let's just, in the end, you probably want to know, okay, great. Now you flip it. Now that once you flip the switch, now the capacitor is discharged. So you want to know what is the charge at some time after the initial event of flipping the switch, right? So for that, you need to say Q equals Q0 e to the minus t over RC. And this Q0 is the time at t equals 0. How do you know that? It's very easy because you just take t equals 0, e to the 0 is 1, so Q equals Q0. So what is that? That's this value right there, 120. So then you stick 0.3 seconds in here, and then you get the charge at that time. And it comes out to this much. Okay, so you got to multiply t, RC is 0.2, and then they're asking you at 0.3, so 0.3 divided by 0.2, e exponential of that, and then you get this. So it's not 120, it's already decreased by a whole bunch. Okay, so that's how we analyzed the circuit. Any questions about this? I'm going to put just one multiple choice question just like this. Now, I could, for instance, well, let's do the opposite. They have it here. I'm not going to tell you which one. I'll do one or the other, but you'll still have to think about which one it is. It's not too much, but you could do it the other way. So let's do it. Let's do it very quickly because I will have one multiple choice question like that. Let's do this very quickly. They have another example here where they do the opposite. Instead of switching from A to B, they were on A here, and then they put it on B. Now they do the opposite. They start at B for a long time, and then they switch it to A. Okay, so how would it go? Well, it's the same thing. Where is it? It's right here. So they start in this condition. So they want you to know is you start like this. So then what is going to happen is the capacitor will discharge over, just keep it like that. So the capacitor will discharge. When it's fully discharged, the current will be 0 again. So there will be no voltage. In this case, you're discharging the capacitor completely. So you start at charge equals 0. But the current right before the switch is thrown is 0. Okay, now they say, okay, now we open now we put it here in this, we flip it the other way, we put it on A. Now, what is the current then? Right after you flip it. Well, now in this case, it sounds like you're doing the same thing. It's not the same thing. You started in this problem, in the second problem here. I'll put this up, actually, what I'm gonna do is, after I'm done with this, I will definitely put this same one on Canvas to make sure, if something is a little confusing, you wanna make sure that you got it, just go to Canvas, I'll have this up there. But in any case, so what you're doing here, in this case, you start out with 0 charge because you were at B for a long time. You fully discharge the capacitor, and the one above, you fully charge the capacitor. Here, you fully discharge. Okay, so therefore, since it's fully discharged, there is no voltage across the capacitor at time t equals 0. The voltage is 0. So therefore, the voltage, once you close it here, you can go around the loop. And whatever the voltage is here, that must be equal to here because this is 0. The capacitor is fully discharged. So right after you close it, then you must have IR equals VB because VC equals 0. That's right after you close it. And so therefore you can find what the current is. So now I say, what is the charge on the capacitor? 0. That's what we just said. It's fully discharged. That's not the same as above. Okay, and then you say, how about right after? Still 0. Okay, so now what changes now is you cannot use the formula for the capacitor changed because you cannot use the discharge in the capacitor formula. You're not discharging the capacitor now. Now you're charging the capacitor. You start out at 0 and you get to some value. So notice this formula. Make sure that if it's not quite clear what I'm saying, make sure that you check that, because see, this formula here is not the same as this formula. The one at the bottom is 1 minus E. That's the charging capacitor formula. This is the discharging the capacitor formula. They look very similar, but it's not the same. It's 1 minus. You see there is this 1 minus in here. This is not above. It's 1 minus the exponent. So based on that, we can figure out how much charge there is after some time on the capacitor. Okay, anyway, so you'll have to figure out in the exam, you'll have to figure out, is the capacitor, based on that, you use the discharging formula or the charging formula. It's not a lot, but you'll have to do it to solve this multiple choice question. In this one, the Q0 is the final charge. So this Q0, the way to do this is to figure out what is the charge at any one time. So if you put Q equals 0, you can put, you don't need to, let's see what they do here. What is the charge on the capacitor at time t.3 or the switch is thrown? So you put the t equals here, the Q0, okay. Yeah, you have to, yeah, they didn't tell you how to do it, but I can tell you how to do it, but they don't show you how to do that. Yes, very good point. Thank you, Emma. Absolutely, they don't show you how to do that. So that really screwed it up. And I almost screwed it up as well until Emma told me that I need to do more work. That's correct. So how will you know Q0? Without knowing Q0, you're not gonna get an answer. You must know Q0. So how will you know that? So to know Q0 in this formula, Q0 is the final charge on the capacitor. The initial charge here is 0. Okay, so Q0 is a little bit of a, okay, so good. I'm afraid I'm gonna get you confused. Instead of Q0, let me rewrite this formula for you. And we're gonna find how to do it. Okay, it's Q. Instead of writing Q0, let me write Q final. And I'll tell you why I'm doing that. Q0, normally people use 0 means the initial. Okay, but this is not the initial. This is the final. Let me show you why I know that. So that's why when I saw that formula, I was like, what are they talking about? Q0 would be 0. If you put Q, that's not correct. This is Q final. So how do I know that? Because if I put t equals 0 into this formula, I get 1 for this term and 1 for this term, and I get 0. I don't get anything. I get 0 equals Q equals 0 from this formula. So, but how about if I put t very large? If I put t very large, then I get Q equals QF. The second term will be, so t going to infinity. This second term is 0, and the first term is the only thing I have left. So for t going to infinity, Q equals QF. Okay, so what is QF? Still haven't answered that. You don't use Q0, though. That doesn't make any sense. That gives you 0, and that's stupid. Okay, so very good question, Emma. Thank you so much for that, because otherwise this would not be clear. So how do you get QF? So QF is the final charge of that will be on the capacitor once you've left it hooked up to the capacitor to the battery for a long time. So in that case, once again, the current will go to 0, and QF will be equal to C times the voltage across the battery. So that's the charge you have to put in there. Okay, so you put that charge in there, you put it in here, and then you put this t of 0.3 seconds into the formula. Does that make more sense now? It's not Q0, Emma. That's a fantastic question. It's QF, the final charge. Q0 is 0. QF is the final charge on the capacitor. Okay? What you really needed there is the final charge. So yeah, that's the kind of thing that immediately throws you for a loop if you're doing it in the exam, because now you have to start thinking, and that's you know, in exams thinking is hard. You just do things, but thinking is very hard in an exam. Okay, anyway, I will definitely put this online. Please check it out. Make sure you got it. You know what we could do? We don't have class on Friday, but maybe what we could do is, for those of you, I feel a little bad. I'm going through things a little fast. Maybe you're not ready to ask me questions. How about if we could possibly have office hours on Friday instead, a little closer to the exam time? If I could pick a time that everybody would be available, we could do that. Let's start. Let me suggest a time, and if it will be no good for you, the only problem with that, I think it's a good idea. Obviously, some of you would like that, but the only problem with that is that if I schedule a time, it might not be good for somebody. So let's give it a trial. Try to make it work. So how about? Let me think. Do I have teach? Okay. How about during the regular class time? So starting at 1:30. Does that work for everybody that wants to do it? If somebody cannot do it, let me know right now. I can't schedule something that somebody cannot make it, but if I can make it at that time, so we can have like office hours during regular class time. If you can't do it, please let me know. Okay, so let's do that though. I'll have it. I'll log in and so on. I'll send the class email with the link. Okay, yeah, let's try to do that on Friday. But again, if somebody has a problem with that, I'll have to try to reschedule and so on. So it could end up being a mess. But I'm not getting any negative feedback, so I guess we'll give it a try. Okay, anyway, so yeah, check this out because that's definitely the case. You need to know what QF is, not Q0. Q0 is 0 for this problem. But QF is given by this, the final charge on the capacitor. And so you can definitely find that. Then you stick it in there, and then you can find the charge at any time from that. So this is wrong, obviously. Q0 is not Q0. Sorry about that. Okay. Okay. So yeah. Well, since we have a little extra time, then let's see what else we can do here. Oh, by the way, these two things are already on Canvas. So let's try one of the two. This motor quiz is also on Canvas. Let's try this one here. You will have. Yeah, let's just do this one. Say, for instance, right here, this one. Try. I mean, I don't know if this is the best one to do, but in the exam there will be a bunch of questions. Remember that I said I would do this, which is to write, do a diagram. It's a little bit like that, like this. So you would have in this diagram here, you would have this is the North Pole, this is the South Pole. So you have a B field going this way. Okay, so remember that when you have this kind of a diagram, there are multiple questions you can ask. You can ask, what is the force? So one of the questions you could ask is, what is the force on the sides of your loop? So what is the force here? What is the force here? What is the force here? Because there is a magnetic field and there is a current, right? So you can ask about forces. You can also ask about torques. Are you twisting the thing, yes or no? And you can also ask about fluxes. Is there a flux through the loop? Do the arrows go pierce the loop? Yes or no? So those are the things you can ask about, and I can tell you right now that there's a question about each of those in the exam. This setup, is there a force? Yes or no? Is there a torque? Yes or no? So is the loop twisting? Yes or no? Is there a flux? How much? Okay, so there will be questions for each of those based on my diagram. Okay, so let's start with this, and then we'll continue, I guess. Yeah, we'll continue. And please bring your questions to the practice thing. We can do the one about, we can just go through the problems I told you are going to be in the exam. But let's try this one first. And you tell me, what do you think is the answer to this? To this one. Let's work on that one. So it's a normal to the surface area is perpendicular. There is a current flowing. What is the force acting on section BC of this coil? Okay. So remember force. Now I like to write it differently, but I'm gonna keep writing it my way, I guess. That's the force. So you have to figure out. So what do you think? What is the answer here? Okay, so we agree on B, right? Okay, that's right. And again, you have to go back to the formula for each case. So you have to be careful. What is the question asking exactly? You could ask this piece, that piece, or you can ask fluxes, or you can ask torques. So the force on this piece is 0 because the current is aligned with the magnetic field. Okay, let's go. Let's do. We don't have that much more time, but let's do a few more, and then again we'll be stuck. How about the next? Let's. So it's kind of like this format. Oh yeah. Let's do this one as well, and yeah, let's do them all, and then and then we have to stop wherever we get to, and then we'll have more time to continue afterwards. So let's do this one. This is already on Canvas. I said that. Let me say it again in case. So we're on question 4 now. Okay, number 4 now. What do you guys think? Still B, right? Yeah. Remember what is the angle, right? So the angle you're doing cell I cross B. So the angle is the angle between the current, in my case, the direction of the current, and in the book they would say the direction of the wire, which is the same as the direction of the current. So that's why I like to write it this way a little better. So the direction of the current and the B field. Well, the angle between those two, between A and B, that's 90 degrees. So you don't, so it will be ILB. Okay, so this is the answer, P. Could it be A, B, or B, A, B, or single is 90, so we give the same answer. So the current goes this way. The B field is this way. So you're asking, couldn't it be A or B? No, it's from A to B.
Let me clear up my question.
Oh, yeah, sorry. I didn't understand that. Yeah, go ahead.
So I'm saying it could be answer choice A or answer choice B.
Yeah, because they don't say what sign is, the angle is. Okay. So you don't like the question, that's what you're saying.
Well, I mean, it's a little confusing because technically it could be the same.
Yeah. They don't. Okay, fair enough. Well, it doesn't make a difference because that's not how I'm going to write it in the exam, but yeah.
Okay.
That's your point. You could say, since they don't tell you what it is, then it could be A2. Okay, fair enough. Okay, let's do this one then. Please try to do it right now, in fact, because there's something very similar to that in the exam as well. So try to figure out, remember, in fact, go to your notes right now, just to make sure you don't spend a lot of time looking through notes at the time of the exam, and figure out how did you figure out the radius of curvature of a particle moving in a magnetic field? So we'll stop here. This will be the last question we do, I guess. You have to remember how to get the radius of curvature in order to answer that question. If you get when you get the answer, please give the letter that you know how to do it. So you tell me your letter. Okay, that's right. So all you have to do is what Isaias wrote. So let me just remind you of how he got that. You can find that on your notes, but let me just remind you of how we did that. How we decided what the radius of curvature was going to be. And then you get what the formula that he has in there in the chat. And then you just plug in the numbers. Once you have that formula, it's easy. You just plug in the numbers. But in case you forgot about that formula, this is how we got that formula. Let me remind you of that. What we did is we have a force on the charge, which it goes like the velocity. So the cross, there's a sign there, of course, but the sign is just one because they're perpendicular to each other. The B field is perpendicular to the velocity vector. Okay, so then we have the force was just QVB because of that, because they're perpendicular for the setup that we have. And then, what it turned out to be the case is that the particle moves in a circle. And so we have the formula for the acceleration in that situation, which is equal to v squared over r for the acceleration, where r is the radius of the circle. Okay, and then you just solve for r. Okay, the v cancels. I move the r to the other way, and then I get mv over qb, just like he has. So there, at that point, is just plugging in the numbers. Okay, so this came from the acceleration of a particle moving in a circle. Centripetal accelerations, like in physics 50. Okay. So remember that, yeah, you're gonna have that in the exam, and you have to remember whether it's positive or negative, which direction will it go, and what is the mass. If you have remember that for protons and electrons, they have the same charge, but they definitely don't have the same mass. A proton is much more massive than an electron. Okay. So that's going to be it for today. I didn't get anybody to tell me I couldn't do it on Friday. So since it sounds like everybody can do it on Friday, then I'm definitely going to try. I'm going to do it Friday. Unless I get some severe objection from somebody, Friday it is. Okay, so Friday during regular class time, I will have office hours. I will send an email to remind everybody with the link as well. Okay, so see you guys Friday. Hopefully we'll all show up. See you then.